Mole.
This mole is a fun character controller demo I made with the help of some friends and my OpenKCC library. The project was inspired by a demo that my friend showed me. They were discussing some problems they ran into when they were making this mole character movement with another character controller library, and as they described their difficulties, I realized that my OpenKCC library didn't have those same limitations and offered to help build a demo for them. I told them it would probably take a week or so to get the demo up and running, and as all software engineering guesses, I was very wrong. It only took 48 hours! But then it took like 2 months to fix all the bugs. But let's not talk about that. So what makes this mole movement so unique and difficult to make anyways, and why did it only take me 2 days to take the demo when I thought it would take a week or more? Well, when a character normally moves around and runs into walls, they stop. However, this mole on the other hand should smoothly climb up the wall. You can even go upside down if you want. At first, this may seem daunting to recreate, just, run into a wall and then climb, but after some investigation, I found it was actually really close to some of the code that I had already written. So previously I had written code to snap a player down onto the ground whenever they were walking downstairs. This kind of algorithm also works for keeping the mole's feet glued to the ground, but instead of snapping the direction of gravity down, I need to snap him toward his nearest surface. This could be achieved by just overriding the up direction of the movement, and it worked right away. The trickier part was ensuring that the mole's movement felt natural. Since the mole can move along any surface, the camera might not always point in the correct direction. So I needed to make sure that the mole would move in the proper direction. However, there's still one big part left, which is how should the mole move when they walk into walls? When the player normally walks around, we rotate their input along the camera's yaw rotation, or rotation of the vertical axis. However, with the mole character, this doesn't quite work the same, because the vertical axis isn't always the same as the up direction of the mole. But wait, that's it. We adjusted the up vector to make sure that the mole snaps to the ground. We can use that same up vector for rotation and computing which direction the mole should move. Easy. And that realization right there is why I was able to finish ahead of schedule. Such a rare occurrence. The double use of the surface normal for snapping to the ground and computing what direction the player is looking made this problem relatively trivial to implement. However, that's the kind of weird part of it. You probably heard the word surface normal, quaternion, and your brain just maybe grinded to a halt trying to visualize that four-dimensional transformation and how rotation is modeling, so let's not think about that. The math behind the mole movement in 3D space is complex, so let's try to look through a simplified example and visually go through what's happening in this behavior. In the Unity game engine and other 3D modeling engines and softwares, there's this concept of the rotation of an object. This is usually defined as a quaternion, which is a matrix. However, computing this quaternion for our mole depending on what surface we're on can be a bit daunting. There's another way to define a quaternion instead of the matrix, by simply using the three vectors, a forward, up, and right vector. Technically you only need the forward and up, but having the right vector helps keeps it from randomly flipping backwards. So if we can identify each of those components, we can identify our mole's rotation to figure out how we should move. Normally a character can only modify one of their axes of rotation, the rotation along the vertical axis, also called the yaw, by turning left and right. However, our mole also needs to be able to move along another axis of rotation, the horizontal axis and the vertical axis, pitch and yaw, to handle walking up and down any surface. Now, a character would normally have the vertical axis be the direction of gravity, up and down, and the horizontal plane is simply the x-plane. However, this is not the case for our mole. You may remember that I mentioned up vector and the surface normal. The normal vector of a plane is a vector that's perpendicular to that plane. For our mole, we need our rotation to be along the surface that the mole is standing on. We can achieve this by using the surface normal of the plane that the mole is standing on as the vertical component. This allows us to stay on the plane, but doesn't quite tell us what direction we should rotate when the player turns. For the non-mole character, we simply move in the direction that the camera is looking, but for the mole, if we were to do that, we'd probably end up walking into or jumping off of walls a lot unintentionally. So by using that surface normal as the up vector, and the direction that the camera is rotated about that up vector to determine which way the player should move, we can compute the forward vector and the up vector of our mole's rotation, and then from that we can compute the quaternion using Unity's quaternion.lookRotation magic function. Now that we have that lengthy design and linear algebra discussion done, how does this code actually work? So when the OpenKCC normally operates, it uses a bounce and slide mechanic where the player will stay in the same direction and slide along whatever surface they're hit. However, the mole needs to turn their rotation and rotate their feet to face the wall that they're walking on and then slide up that wall. I've dubbed this kind of movement bounce and rotation instead of bounce and slide. We have that algorithm from earlier to compute the rotation of the player based on the surface normal. We can simply apply this algorithm each time the mole wants to move to a new surface. However, this begs the question, how do we know when the mole wants to change to a new surface? And what is that new surface anyway? All jokes aside, this is fairly simple. We just need to check when the player runs into a wall. And every time they run into a wall, that's their new surface. My OpenKCC API allows you to interrupt movement when the character hits something and redirect the player movement using iterator and yield design pattern in C#. When the player hits the surface, it'll interrupt the code and yield the current bounce information. Normally, we use this bounce information and then slide based on the surface we hit. However, we can override this movement by computing the new rotation and pass that back to the rest of the player movement. Between and after bounces, we do need to keep track of our surface normal and up vector to make sure that we're always moving in the right direction. But this kind of overriding and interrupting the previous workflow is much simpler than recoding and duplicating all that behavior from before. And after just spending far too many hours debugging, bam! Mole movement with our bounce and rotation algorithm. If we translate the player's input to the axes and plane that the player is standing on, we can allow them to move both forward and backward as well as left and right. However, there's one important factor I left out here, and that's camera controls. Normally the camera should follow the player and rotate with the player's direction of movement. I mean, it sounds simple enough, but for this mole that can climb up and down objects, it can lead to some really complex problems. To make this problem, simpler, I have the camera always aligning with the world's vertical axis. Never allow the camera to rotate past 90 degrees, as that can sometimes lead to motion sickness. This way, the camera follows a more traditional 3D platformer style, and to achieve this, we simply need to move the camera to follow the mole and then just simply translate it back a bit. There is a more complex solution that would allow the camera to roll with the player, similar to Super Mario Galaxy, so that it always faces the correct direction. But sorting out all that math and information is going to be left for future video. This basic solution works well enough for now, however it does break when the trier tries to climb upside down something. So remember way back at the start of the video when I mentioned that a quaternion has 3 components, up, forward, and right? Well, it turns out that a single set of forward and up vectors actually can define 2 quaternions, one for each of the right directions that the right vector can point. How should we decide which right vector to use? I mean, it'll determine which way is right from our input, and if it's the reverse of what we expect, we just keep on going the wrong direction. So since I simplified my character controller to always assume that the vertical axis is up and not the player's up, I can't really fix it. It would involve allowing the camera to rotate past 90 degrees and flip upside down, which can get really nauseating if not handled properly. We can use the global up vector to compute the right vector, and this works whenever the surface is facing up. Smoothing the mole movement and keeping it at the correct vector ensures that the player doesn't flip around by accident and that all movements perform as expected. This results in the movement direction being inverted when the player is upside down. So to get around that, we can switch, instead of using the up vector, we can use the down vector when the mole is upside down. And then we can change this whenever the player swaps between an upward and downward facing surface. And if we want to just avoid this kind of jittery behavior when it quickly switches between those 2 directions, we can add some small threshold angle or a large threshold angle between swapping them. This would ideally be replaced by the more advanced camera controller, but that would take a long time to program, and we still need this kind of camera movement for when the player isn't digging. Speaking of a long time to program, you probably noticed that all the pretty particles that the mole throws up as they dig, they're a pretty cool effect and add a lot of life to the character. If you look closely, you might have noticed that the particle colors change based on what the mole's digging in. This is achieved by setting up a particle system that creates little cubes that will slowly shrink over time, and these particles are created as the mole moves around. An important part is to attach the particles to whatever the mole is digging to and make sure that we update the color. Otherwise, they just float away when on a moving platform and the color mixing wouldn't look right. For the colors, I have it do a gradient mixture between an earthy brown color and the platform color. It helps add that extra realism effect and emphasize what you're digging into. There's also a second set of particles that are dug up around the mole while they're moving, and they just go in a little circle around the mole whenever you're digging, just to show that you're digging. This is great and all, but it leaves out one important detail. How could we leave trails across multiple objects? I mean, if we attach the trails of particles to every platform we cross, it would suddenly start teleporting and moving around if we tried to attach it to everything. To get around this issue, I actually create 10 sets of trails and quickly switch between them whenever the mole attaches to a new surface. And whenever the mole leaves the ground, we simply have to stop the current trail that we're digging. There also needs to be a small offset between the particle position and the mole position to keep it looking like the mole is grounded despite the collider being above the ground. You see, the mole is actually a little sphere on top of it, which is how we can get away with all that rotation magic, but the model should be in the ground to give that effect of digging. So there's still a lot more left to do with this project. I have to overhaul that camera system and add all those features I was talking about. And, we probably want the mole to be able to walk or run instead of just digging everywhere. Right now, the movement engine is open source, and you can check out the live demo at the website in the description. This supports multiplayer, but getting into how all that works is a whole nother video. There's a lot of fun extensions to this project. My friend that originally sent me the demo for the mole characters are going to try and start making a full game sometime in the next few months. They told me they might post some videos on their YouTube channel, Deep Sea Learning, when they get the chance. Make sure to check out their videos if they've made them by the time this video goes live. I hope you found the mole character interesting. Try it out for yourself, and if you have any suggestions or questions, feel free to leave a comment under this video, or an issue on the GitHub page if you have any suggestions. Have a great day!